Hello. Can conventional wastewater treatment really remove everything? There are occurrence of emerging contaminants such as antibiotics, hormones, PFAS, pharmaceutical residues, personal care products, microplastics in the treated wastewater as well as water samples. The answer might surprise you. Today, we will explore one of the most powerful technologies transforming modern water treatment, which is advanced oxidation processes. So stay till the last. Water pollution is changing with time. The type of pollutants which are being received in any wastewater has also changed. The conventional wastewater treatment plants were mainly designed to remove pollutants such as suspended solids, organic matter, pathogens, and nutrients. But today we are facing a new generation of contaminants known as emerging pollutants. I have a separate video series on emerging contaminants. But what are emerging contaminants? These are the new generation contaminants or small molecules such as antibiotics, pharmaceuticals, pesticides, endocrine disrupting compounds, personal care products, industrial dyes, and PFAS. These compounds persist in the environment and are extremely difficult to remove using conventional treatment technologies. And that's where advanced oxidation processes come into picture. Advanced oxidation processes represent the next generation of water treatment technologies capable of destroying contaminants that conventional systems cannot handle. So, the traditional wastewater treatment systems perform remarkably well in removing many pollutants such as suspended solid, biodegradable organic matter, pathogens, nutrients such as nitrogen and phosphorus. However, the problem arises when we deal with complex and persistent contaminants. Conventional treatment plants usually struggle to remove pharmaceuticals, antibiotics, PFAS, endocrine disrupting compounds, textile dyes, and numerous industrial chemicals. The consequences of these compounds present in residue are significant. They may lead to ecotoxicity, development of antimicrobial resistance, groundwater contamination, bioaccumulation, and potential human health impact. This growing concern is pushing researchers and engineers toward advanced oxidation technologies. So, advanced oxidation treatment technologies are the techniques that generate highly reactive oxidizing species capable of degrading persistent contaminants. There are different radicals or oxidizing species which get generated in an advanced oxidation process, but most important among them is hydroxyl radical, represented as OH. So hydroxyl radical possesses an oxidation potential of approximately 2.8 volts, making them among the strongest oxidizing agents known in environmental engineering. Unlike the conventional oxidants, hydroxyl radicals react extremely rapidly with pollutants. They can attack complex organic molecules and break them down into simpler compounds, and in many cases, they can achieve complete mineralization. That means converting the pollutants into harmless end products such as carbon dioxide, water, and inorganic ions. So let's understand how advanced oxidation process actually work. The process can be divided into four stages. The first stage comes radical generation. Hydroxyl radicals are generated through various methods such as ultraviolet light, hydrogen peroxide, ozone, iron catalyst, or electrochemical reactions. Next, these radicals attack the pollutant molecules. Because hydroxyl radicals are highly reactive, they rapidly interact with organic compounds. The third step is fragmentation. Large complex molecules break into smaller intermediate compounds. Finally comes mineralization. The intermediates undergo further oxidation until they convert into carbon dioxide, water, and inorganic species. This ability to destroy the pollutants rather than simply transferring them from one phase to another is one of the biggest advantages of advanced oxidation process. because in other techniques such as adsorption or membrane-based filtration, the the pollutants are not actually degraded, they are just transferred from one phase to another, which again needs further treatment. But in case of advanced oxidation processes, the compounds are degraded, and that's why it is advantageous over other processes. So, hydroxyl radical possesses several remarkable properties. First, they can extremely high oxidation potential. In fact, they are stronger oxidants than chlorine, ozone, hydrogen peroxide alone. Second, they are largely non-selective. This means they can attack a wide variety of organic contaminants simultaneously. Third, their lifetime is incredibly short. They react almost immediately after being generated. And finally, they provide high degradation efficiencies and rapid reaction kinetics. Because of this characteristics, hydroxyl radicals have become the backbone of advanced water treatment technologies. There are several important types of advanced oxidation processes currently being used and studied. Briefly, there are Fenton processes, which involve the reaction between iron ions and hydrogen peroxide. It is relatively inexpensive and highly efficient. Then there are Photo-Fenton processes, which is an improved version of Fenton processes. Light irradiation enhances the radical generation and improves degradation performance. Then there is ozonation. Ozone is used as a strong oxidizing agent. It can directly oxidize contaminants and also generate hydroxyl radical. Then there is photocatalysis. Materials such as TiO₂, titanium dioxide, are activated by ultraviolet light or visible light irradiation. This produces reactive species capable of degrading pollutants. Then persulfate oxidation. Persulfates generate sulfate radicals, which are also powerful oxidants. Then electro-Fenton processes. Electricity is used to continuously generate radicals within the reactor. Then plasma oxidation. Cold plasma technologies are emerging as promising methods for further water treatment applications. Each of these advanced oxidation process has its own advantages and limitations, energy requirements and treatment efficiencies. So what can advanced oxidation process remove? One of the most exciting aspects of advanced oxidation process is their versatility. They can remove a broad spectrum of contaminants such as pharmaceutical compounds, pesticides, PFAS, textile dyes, hormonal compounds such as bisphenol A, and even microplastics and industrial chemicals. Because of their broad applicability, advanced oxidation processes are increasingly being considered essential technologies for further wastewater treatment plants. Advanced oxidation processes are already being implemented worldwide. In India, several industrial clusters are adopting advanced oxidation technologies. In Gujarat, common effluent treatment plants are using advanced oxidation to remove recalcitrant pollutants from chemical and pharmaceutical industries. The textile industries in Tirupur employ advanced oxidation processes for dye degradation. Hyderabad's pharmaceutical sector is exploring advanced oxidation process to remove antibiotic residues and combat antimicrobial resistance. Internationally, Singapore's new water program utilizes UV and hydrogen peroxide system to produce ultra pure reclaimed water. Japan's employ advanced oxidation technologies for wastewater reuse applications. Meanwhile, US and European countries are actively investigating in PFAS destruction technologies and advanced oxidation treatment system. These developments highlight the growing importance of advanced oxidation process in achieving sustainable water management. So what does the future hold for advanced oxidation process? Researchers are now focusing on solar-driven photocatalysis, visible light responsive catalysts such as graphitic carbon nitride or modified titanium dioxide are receiving considerable attention. Another promising area is metal-free catalysis. Materials such as graphene, activated carbon, or biochar may provide cost-effective alternatives. Artificial intelligence and machine learning are also entering the field. These tools can optimize operating conditions, reduce energy consumption, and accelerate catalyst design. However, The challenges still remain: energy requirements, chemical consumption, catalyst recovery, and large-scale implementation continue to be the areas requiring further research. Conventional wastewater treatment plant alone is no longer sufficient to address the complex contaminants emerging in today's world. Advanced oxidation processes offer a powerful solution. They provide rapid degradation, high efficiency in treatment, and potential for complete mineralization of pollutants. As water scarcity increases and water reuse becomes important, advanced oxidation processes are likely to become an integral part of next generation wastewater treatment systems. What do you think will dominate the future of water treatment? Photocatalysis, ozonation, or electrochemical technologies? Let me know in the comments below. If you enjoyed this video, don't forget to like, subscribe, and share it with fellow environmental enthusiasts. Thanks for watching, and I will see you in next episode of Clean Cover Talks. Till then, tata, bye bye, take care.